In this video, I wanted to do a little bit of a different example. This is just comparing different magnitudes and values that we get by taking the length of different vectors, the dot product, and then also looking at the cross product of different vectors. So the setup for this problem is that we're going to use these two sets of vectors here that are labeled A through E, lowercase and capital letters. And some things to note is that our lowercase letters all have unit length, and our uppercase letters all have length 2. And then finally, another really important piece of information is that all the angles between the vectors are multiples of 45 degrees. Okay, so let's go ahead and get started. We'll jump right in with part A here. They want us to put these values in order from smallest to largest. So just to kind of recap on notation, length of u, well, let's just, so length of the vector u. So length of A, we're actually already told has length 2, so I'll just put a little 2 there. And then same idea for length of lowercase a, we're told that that is equal to 1. So those two values are pretty straightforward and simple to find. They're just given to us. The ones that take a little bit more work are going to be where we're taking the difference between two vectors. So A minus E, how are we going to look at that? Well, to compute A minus E, what that would look like is taking E and then flipping it over and then drawing it on the other side of A. So that's going to do something kind of like this. So this whole thing here is A minus E. So then its length is really just the length of A, which is 2, plus the length of negative E, which is again 2. So that's just equal to 4. We can apply the same idea in finding C minus E and D minus E. So drawing a flipped over copy of E up here with C. We can find C minus E by drawing the vector that goes from the base of C out to the end of E. And we know the length of C to be 2, and we know the length of negative E to be equal to 2 as well. And we also know that this angle right here is a 90-degree angle. So this means we can find the length of C minus E by taking the square root of 4 plus 4, which is equal to root 8, or more simply, to root 2. So that's that one. D minus E, we can find the same way, but this one's a little bit trickier because it won't be quite as easy to see how all the pieces fit together, but that's okay because we actually don't need the exact length in this case anyway. So D minus E is this little segment right here, going from the beginning of D to the end of E. And notice that that vector is actually shorter than the vector B. Well, that means that this has to have length less than 1. And that's really all the information we need to know because this is the last vector we're finding, and we know that all of the other ones are at least 1. So to put these in order, we know that we first have the length of D minus E, that's the smallest, followed by the length of lowercase a, which is less than 2, which is length of uppercase A, which is less than 2 times the square root of 2, or the length of C minus E. And then finally, that's less than the length of A minus E. So that kind of just puts all of those in order like so. We're going to kind of apply the same idea in the next two where we're going to compute exact values for each of those terms and then see how they line up. Okay, so for our dot product here, we want to remember that the dot product of U and V is equal to the length of U times the length of V times cosine of the angle that is between them. So this is where the idea that all the angles between the vectors are multiples of 45 degrees becomes really important. So if we look at A dot E, for example, I'll write all the values out here. Well, this is equal to the length of A, which is 1, times length of E, which is 1, and then cosine of the angle between them, which is just 180 degrees. Well, cosine of 180 degrees is equal to -1. So that whole thing is just -1. Same idea with A dot D. It's 1 times 1 times cosine of, this angle here is 45 degrees. So 180 minus 45, that's got to be a 135-degree angle. Cosine of 135 is actually equal to -√2 divided by 2. So that's our answer for that one. A dot C. This one's actually pretty easy because the dot product of two vectors that are perpendicular to each other is always equal to 0. So since A and C are perpendicular, that's just 0. And then A dot B is 1 times 1 times cosine of 45. Cosine of 45 is √2/2. So that's what we get for A dot B. And then finally, A dot A is equal to 1 times 1 times cosine of 0. Cosine of 0 is 1, so that's just 1. So it actually turns out that all of these were already written in order. So let's put that here. From smallest to largest. But the big takeaway here is that anytime that you have two vectors that kind of point in opposite directions, like A and E and A and D, how they kind of point away from each other, you're going to wind up with negative numbers. With more negative numbers, or greater negative numbers, I guess, if you will, like this -1 here, when they're actually still parallel to each other but facing in opposite directions. Anytime two vectors are perpendicular to each other, like A and C are, their dot product will be 0. And then the greatest dot product is achieved when you're taking that vector dotted with something that actually points in the same direction as it, either that particular vector again, or maybe a scaled version of it. So that's pretty much all there is to working with the dot product case. And then finally, let's do the cross product. And the big idea behind this that we're going to want to use is that U cross V, and then we take the length of it, because remember the cross product gives us a vector back, but we can't compare, say, which vector is greater than another vector or anything like that. We have to take the length to be able to talk about that kind of thing. The length of the cross product is length of U times length of V times sine of the angle between them. So again, very important that all the angles between the vectors are 45 degrees. So let's compute A cross E. So in this case, we have 1 times 1 times sine of 180. Well, sine of 180 is equal to 0. And this kind of highlights something that's really important with working with the cross product. It's kind of flipped from the idea of the dot product, in that anytime two vectors are parallel, we're going to get 0 out of it. So something to keep in mind there. So for D cross A, that's 1 times 1 times sine of 135. Sine of 135 is positive √2/2. And then A cross C is 1 times 1 times sine of 90. Sine of 90 is 1, so that's equal to 1. And then looking at capital A cross capital C, we're going to get the same idea, except our magnitudes this time are 2. And we kind of see, again, the opposite pattern of what happened with the cross product, where when two vectors were parallel, we got 0, and then when two vectors were perpendicular, we got the larger values. So just bear in mind that cross product, or the length of the cross product, is maximized when the two vectors we're working with are perpendicular, and then minimized when they are parallel to each other. But that's pretty much all there is to working with these kinds of problems. Again, the two important formulas for at least working with the dot product and the cross product were that the length of U cross length of V is equal to the norm of U times norm of V times sine of theta. And then a similar one for the dot product, except instead of sine, we get cosine. And that's pretty much all there is to this.